So I'm sitting in an empty classroom because apparently students feel it's no use revising with teachers before their exam. I will never understand that. So I need to ban this class from being absent. Who are we? Let's see. Alright, as usual. Okay, what are we doing? Now, we're going to continue with these questions. I'll try to finish the rest of these practice problems. Over here, we've got a question asking for the current in the 20 ohm resistance in this figure. So you need to understand that the 20 ohm resistor is in the same path as the battery. So I will actually need to calculate the total current for that one, because afterwards it will split into the 40 and into the 40. Actually, it will split equally because they're both equal resistance. It's not asking for individual resistor. Because it's specified 20, it's not going to be I is V over R, 60 over 20. That will be wrong. It will be V over R. It will be I equals V over R, of course, but it will be V over R total. I will have to do 60 divided by the total resistance. Now, if you followed my previous video, you should know that if I have two resistors in parallel and they're equal, the total resistance here will be 20 ohms. 20 ohms. That was a fail of a word, number 20. All right. If these are both 20 ohms in parallel, they are in series with this one, because the junction starts here. So these two are parallel 20. It'll be 20 plus 20 over here as well. So it'll be 20 plus 20. That becomes 40. 60 over 40, well, 6 over 4, you'll get your answer, will be 1.5. So that's how you will find it. You will calculate the parallel resistance, and if they're equal, then that makes it so much easier for us. Once you've done that, you add it to the series resistor, and you'll get your answer. Okay, let's move on. Over here now we have a circuit here, which looks a bit complicated, but actually it's not. You're trying to find the current flowing out of this battery again, so this is now specifying the current from the battery. It did not say the 10 ohm resistor. If it did, it would be in the same thing. I need the total current. We have the current flowing through this resistor, so this resistor is in series with whatever the heck is going on over here. So let's see. We have a junction. Okay, if there's a junction, that means these three paths are parallel to each other. That's path 1, that's path 2, and this is path 3. Path 3 has two resistors which are together. In this path, these two are in series. So actually the resistance in this path is 60. The resistance in this path is 20, and they will meet over here, and they'll come over here. And the resistance here is 40, and they meet here, and they come across here. So if that does not look very easy for you, let's redraw the circuit in an easier way. So let me just get rid of all that. And let's redraw this circuit. This is the equivalent of me having my battery, having my resistor. We don't use American resistors, we're using British resistors, much better. And I'm going to come down for the 40. This is the 40. All right. This was the 10 from the beginning. This is the 40, which is that one here. And then from the junction, I'm here, I'm at the junction now. I will go like that and come down again. Take a guess which one this will be. This is, of course, the 20. Coming here is the 20. And then from the junction, there was another one. So it was kind of actually like here and then down, right? But what I'll do is I'll keep it simple even more. I'll do that and then that, because this is how you've probably seen all of your diagrams up until now. And this is my 40, and this is my 20. And like I said, these are in series. Maybe I'll change the color for this one. And so these are in series, no problem. So that means 40 plus 20, as I mentioned, is 60. 40 plus 20, that is 60. What I'm going to do to find the total resistance here, first of all, you can see that all three of these are all in parallel, then they are in series with the 10. So literally 1 over 40 plus 1 over 20 plus 1 over 60. And if I'm using my calculator, I'll use a little trick, put them in a bracket, put a power of -1 on it, and directly I should get my answer. So when I do that, I should get the answer of whatever I get. I'm just going to do it in one go. I'm going to do plus the series in 10. That's what I'm going to do. And once I get that in total, 20.9 ohms. There we go, done it. Now, current, no problem, that's easy. I equals V over R. V over R, I will do 9 divided by 20.9, and by that I will get 0.43. That would be my answer. So this looks confusing, but actually it's not. It's really simple. If you see a junction, it means you have 3 paths. You can redraw it. That is the junction, and that's my first path, that's my second path, and that's my third path. 1, 2, 3, 1, 2, 3. I hope that makes sense. What happens to the voltage across the resistor R4 when this switch is closed? So of course, well, V equals IR, doesn't it? R and V is proportional. If that increases, that increases. If that decreases, that decreases. Okay. So what do we see? We have another resistor added in parallel. So as you remember, when I close the switch, adding more resistors in parallel decreases the overall resistance. From a question that we did back here, you'd have to go back to the video and check. Basically what we said was adding an extra, like 1 over 10 plus 1 over 10, you'd get 5. But then I do 1 over 10 plus 1 over 10 plus 1 over 10, you would get something like 3 or whatever you would get. It will decrease. My resistance, not this, my resistance will decrease, which means my voltage will decrease. So they are directly proportional with each other. Less resistance here, the voltage will decrease here. Okay, very nice. So let's move on to the next one. This one is another mixed circuit. Which one has the greatest current if R's are equal? Okay, so we have a current flowing through here. Let's say 1 amp, no problem. And I have this one and this one, equal resistances, so we can safely say a half and a half. Okay, so 1 and 2 are definitely not going to be correct. All right, so that's obviously gone. That's going to be gone. And then we come back over here and come back over here, and then you're going to see this one. So they're equal. They're not correct because they're equal. It says greatest. So obviously, if that and that are the same, they're not the greatest. Actually, this technically could be true if these are less. But let's find out. Let's find out. I can see already, but let's check. Here and here. Now look, there are 2 resistors here now. And there is only 1 over here. This 1 amp is going to be split according to the resistance in the branch. This has a stronger resistance than this. In fact, that's 2R, and this is just R. So that is basically double what this is going to be. So if I'm going to divide the current up, this is going to take less. Of course, as you know, R, V over I, should have been I is V over R, doesn't matter. They are inversely proportional to each other. The current decreases, the resistance will increase. So looking at this would actually only take, if you're good at maths and fractions, this will only take 1/3 of the current. This will take 2/3 of the current, the remainder. This is taking less current because the resistance is doubled. Out of the 1, I'm going to have to divide this into parts. So this is going to take less current, this will take more current. As a result, not equal, it is not equal, 50-50, no, because there are more resistors in the top path, it will be less than half. It will not be 50-50, it will be below 50 because the resistance is stronger. I hope that makes sense. That leaves me with just R5 only. So yeah, that was wrong, and R3 and 4 was also wrong. This has actually got the least current flowing through it, R3 and 4. The question might ask that in the exam, might just say which one has the least, if they're lazy with the questioning. So let me erase all of this stuff, get this out of the way, don't need it anymore. I'm going to look at this now. Which combination has the highest equivalent resistance? So actually I shouldn't have erased that because it's the same idea as this. Look, you have this. Actually I should have erased it, doesn't matter, let's erase it. Because what I'm saying is, look at this. This is exactly the same idea as this, which is basically this, which is basically this. So you have 3 branches, right? This is branch number 1, branch number 2, branch number 3. R, R, and R. So in parallel, adding them all, it'll work out to be the same, yeah? So you'll do 1 over R plus 1 over R plus 1 over R. No need to do it. Basically, it is going to work out to be 1 over R, 1 over R, and 1 over R. Let's compare what this will work out to be as. Let's see. Again, branch 1 is R, R, and R. 3 branches, just like over here that we did already. 3 branches, 3 branches, 3 branches. 1 over R, 1 over R, 1 over R. So that is equal. So these 2 are the same. Let's check this. What is this? 3 branches again. 1 over R, 1 over R. And again with the fractions, 1/3 plus 2/3. That's just basically 1 again, right? 1/3 plus 2/3. 3/3. That's 1. 3 over 3 is 1. This is 1 over r, 1 over r, 1 over r. Same. Now let's look at this one. Over here, this is fine, okay. And then we have this branch, a half plus a half. A half plus a half, well, that's r again. R plus second branch, r plus third branch, r. That's again 1 over r, the 2 halves, plus 1 over r, plus another 2 halves, 1 over r. Exactly the same. Same, and same. Trick question. They're all the same. There we go. Nicely done. Okay, let's move on. So over here, the graph shows the data, and you're asked, you see the V and the I, and you're trying to find about the power. So it looks like we're moving on to power questions now, so let's just quickly write them down. So the 3 main formulas we're going to use. PET has been cancelled, which is nice, so we're going to use PIV. We will use PER, P equals I squared R, and we'll use this V squared over R, PIVR. That doesn't work very well. PER, PIV, PIVR. Very nice. So these are the 3 formulas we'll be looking at. V and I, we'll use PIV. It is saying when the bulb is 12, what is the power, I'm guessing? Yeah. So when the bulb is 12 volts here, and we're trying to find the power. So I have 0.8 amps. So literally PIV, yeah? P equals IV. I will do 0.8, and I'll times that by 12. And 0.8 times 12, of course, will give you 9.6. So there we go. If the current through a resistor increases, how does it affect the power? Okay, so we have R, we have I, and we have P. We have the variable current changing, which means the power is changing. The R stays constant, so we'll use PER. P equals I squared R. If the current through the resistors increased by 4. So that basically means if I was to do 1 squared times 1, that will just give me 1. But what I'm doing now is I'm not doing 1 squared. I am now actually timesing the current by 4. It'll become 4 squared. 4 squared times R of being 1, so that'll just give me 16. 16p. So it'll increase by 16. All right. If the power potential across the resistor increased by a factor of 4, how does it affect the power? What is that supposed to be? And if this is talking about the pin, I'm guessing it's just talking about voltage, potential difference. So let's find out. We will do P equals V squared over R. P equals V squared over R. That's the rule we're going to use because we have a resistor and then we have the power. And we're talking about the potential voltage, potential difference. No problem. 4 squared over 1. I'm just setting everything to 1 except the thing I am changing. You'll realize it's going to give you the same thing. 4 squared is 16. And then after this, we're going to have question 45. So we're going to solve this one. And in order to double the power, what should we do? So let's figure this out. If I want to double the power, so we need to see what formula to use in this case here. In order to double the power dissipated in the resistor, so P equals V squared over R. Okay, so doubling the resistance is not going to help. Okay. Doubling the voltage, I don't think so, because doubling the voltage, that's going to be a bit of a problem. If I double my voltage, what will happen is that will quadruple this, so that will not help. Decreasing the resistor by 4 will drop that by 4 as well. Increasing by about 40%, so that basically means what I'm going to do is 40%, so instead of 1, I'll increase by 40, so 1.4 squared over 1. By doing that, I will get roughly double. And that is going to be my answer, C over here. So it's a bit tricky. You just need to remember that this is the relationship. Doubling will quadruple it. Doubling or halving will be the opposite. So that's not what we're trying to do. Actually, half would work. This did not say half. This by reducing by 4. That's why this one didn't work. So if I just did increasing by 40%, so that's 140%, which is 1.4, and you will get your answer. Okay, so 2 light bulbs operating at this voltage. The power is here, the other has a power here, which has the greater resistance. Okay, so you might think that, hold on, right, we got V, we got P, and we got R, right? P equals V squared over R. And basically, if I have a big power, I would have a small resistance. If I have a small power, I will have a big resistance, right? A small power will be a big resistance. You might think that in that case, that means the answer must be the 25 watt bulb, because this is going to be a smaller power, inversely proportional. Bigger resistance? Wrong. Very smart question. I love it. Let's find out why it's wrong. The idea here is we actually have a constant and a constant. These are not changing. I am changing, the resistance is the only thing that is being able to be changed right now. So if I'm solving any of the problems, I must have two variables. If I have only one variable and the other two stay constant, it's impossible. Let me try to explain. If I said P equals IV, and let's say my power, the I was, let's say 5, and my V was 2. Let's just make something up. 5 times 2 is 10. Now what I'm saying is, my power is constant, I cannot change this. My voltage is constant, I cannot change this. So I am now going to change my current. 5 times 2 we know is 10. But if I change the current, if I said that was 4, 4 times 2, that's not 10. And I cannot change the 10, I cannot change the 2. So this is incorrect. This is a formula that cannot be used. We need to find a different relationship. That rule still applies to this question here, when we were actually supposed to be using P equals V squared over R. The problem is, constant cannot change, constant cannot change. By changing this, I cannot use it. I need to find something which has my resistance, which is of course the variable, and maybe one constant. The resistance and one constant. The resistance and one constant. Well, actually, no, this has got two constants, right? This also, well, that's not going to help because there's no resistance in here. So it looks like I'm going to use this rule over here. So when I'm going to compare the current and the resistance, that will help me with the power. So P equals I squared R. Now you can maybe see that this is going to be directly proportional with the power, because by changing the resistance, well, actually what we're trying to do is rearrange the formula, right? R equals P over I squared. So again, same thing, they're directly proportional. Higher power will give me a higher resistance. So actually the answer is B. Just to quickly recap, we could not use the original formula that you would have originally thought, like we did in the previous questions, because this is a fixed voltage, this is a fixed power. This is a fixed power too. So you're comparing these two powers at the same voltage. So we will use another rule. We will use the P equals I squared R. Okay, so now a fixed voltage is applied across this, and an increase in power will result of which the following can be increased. Okay, so again, we have a fixed voltage, and we're comparing the resistance and we're comparing the power of them all. So let's see what we can do here. So we're going to have to, let's try to apply the same logic as before. Increase in power, so that's a variable, I'm changing the power. And looks like resistivity, cross-sectional area, that's the resistance that I'm changing. So there are two variables. The voltage is allowed to be fixed. In this case, I'm allowed to use P equals V squared over R because I have one constant. This will be maybe my control variable. I have my independent variable and my dependent variable. That's the way we wanted to talk about variables. So I have two variables here. I can use it. Let's use it. The resistivity. So I want to increase my power. If I want to increase my power, I have to change my voltage, but it's fixed, so I cannot. I have to reduce my resistance. So what is the rule? R equals rho L over A. Resistivity is rho. If I increased my resistivity, I will increase my resistance, directly proportional. Everything above this line is directly proportional. Everything below the line is inversely proportional. Okay. Increasing the rho will increase my resistance. Increasing my length will increase my resistance. So increasing the resistivity and my length is not going to help. Next, the temperature of the wire is not going to be included. It's not in the formula, so we're not going to talk about it. Actually, the temperature does really affect the resistance, but not in the way that, not in this scenario. What does affect it more is the area. If we change the area, cross-sectional area, increasing this will decrease this because they're inversely proportional. So that means B would be my answer. Because if I decrease my resistance like that, I will increase my power. Same thing, they're inversely proportional. So copper wire has twice the length, half the diameter, carries the same current, If P is the rate of the energy, what is the comparison with the next P? All right, so let's quickly do this one as well. So in this case, what we can use is we have resistance, okay, and then we have power, and we're going to change the resistance, and we have the same current. So that's my non-variable. This is staying the same, okay, that is constant. I have resistance, so I will use P equals I squared R in this case. Why did I choose this? Because we're comparing the powers. We're comparing the powers, which means that this is a variable. It's a dependent variable, and it's going to change depending on my resistance. That's the independent variable, the thing that we're changing. So these two are variables. This is a constant. I'll use this one. Okay, so that's what we're going to do. Now, R depends on the same thing up here. Why am I drawing the arrow there? I'll draw the arrow over here. So I'm going to do this little trick. I've done this in class many times. So I'm going to say everything I will set to 1. For example, if I do R, this is the first one, I'll do 1 times 1 divided by 1. Well, of course, that's just going to give me 1. But R2 is different. The other one is a little bit different because there are some changes that were made. So what has been changed? There is still copper, so I'll consider that as 1. I know it's supposed to be like 1.7 times 10 to the whatever. I don't care. I'm just going to call it 1. And I'm changing the length. I have doubled the length. So I'll multiply the length by 2. I'm dividing that by something. I'm dividing that by area. And what have we done with the area? We have halved the diameter. Halving the diameter, comparing the two diameters, if that was as 1, I'll make that a half. I know it's supposed to be radius, I don't care, I'm going to just do it half. It works because I'm comparing them. By doing this, let's see what happens. If I was to do this, that becomes 2 divided by 0.5 squared, obviously, and you will get an answer. And that will give you 8. So now that means I have realized that this has increased by 8. This is my resistance. My resistance has increased by 8. So if I was to put that into my formula, P equals I squared, I will call that 1. 1 squared multiplied by, not R, not 1, multiply that by 8. Obviously that's going to give me 8. So I have 8P. Now this video is one of the longest ones yet, but we still have 2 questions to do. And let's see if we can quickly get through these 2 questions. In this case, we're asked to find the total power dissipated in the circuit. Let's see if we can find the total power. No problem, because we have a voltage, we have an R, and there's nothing mentioning about current, but you could calculate the current and do PIV if you wanted to, but no need. We're going to directly do P equals V squared over R. The problem is we don't have the R yet. R1 is 9, R2 is 14, R3 is 2.5, the V is 16. Okay, so according to this, well, we have this in series with both of these. So these two are in parallel with each other. So I need to find my total resistance first. So let's quickly go ahead and solve the total resistance. We will have to do 1 over 9 plus 1 over 14. I'll put that in a bracket to the minus 1, and then I'll just add this 2.5 to it as well, plus, in series, 2.5. That's the rule for series resistors. You put that into your calculator, and you will get around maybe it's 7.98 ohms. Once you've done that, we'll put that into our formula for power. So I'm going to do P equals V squared over R. I've written it here, so I'll continue over here. 16 squared divided by 7.98, and then you should get 32.1. Okay, so let's erase that, give me some space. 12-volt battery here. How much power dissipated as heat? Now this is actually internal resistance coming into play here. Some of you have asked me about this, and let's go through it. There are actually 2 ways to solve it. If you have internal resistance, you have the general rule. V total is the V main from the battery plus, not the main battery, the main after the battery is connected, plus V lost. There are 3 ways. And then we made the formula V equals IR plus IR. Essentially, we did IR plus R. So what I can do in this case, I can solve this problem just a couple of ways. The first thing I can do is I can find the key. The key is finding the current. If I find the current, I can solve it to get the power. If I can also find the lost volts, I can also help to find the power. 2 different ways. I'll show you both actually, just so you understand. Let's start with the general way that I think might be the first port of call, is finding the small resistor, IR plus R. So if I was to do this, I have my 12, I have my 0.999, I have my 7.54 plus R. Shift solve, I will get my internal resistance. Shift solve, I'll get 4.472. That's good. I can now find my power with this. How can I find my power? Well, obviously we have the current, and it is if you remember, it's a series circuit. If you realize that I drew this a couple of times in the previous video. So these two are series with each other. That's my internal resistor. Same path, same current. So P equals I squared R. P equals I squared R. Well, that's 0.999 squared times by 4.472, and if I do that, I should get 4.46 watts. 467, I think it is, or something like that. It rounds up, and you will get A. There's another way. Let's try the other way. Let me change my color. Let's see if we can figure out the lost volts. We'll try it from over here. Let's try over here. Okay, so we will do the V total. V total equals V main plus V lost. V total is the battery. V main is once it's connected to the circuit. This is the, once it's connected, what the voltmeter will read. And then the V lost is whatever's lost inside there. The total was 12. The V main I can replace with IR. Yes, I times R, which we have both of. I can do IR. So I will do 0.999 multiplied by R, which is 7.54. I skipped the step, I didn't write out IR, I'm sure you can figure it out, is the V lost. That will be helping me find the lost volts, because I can use that in one of my power formulas as well. So V lost, you can do shift solve or solve that and subtract it from 12. That's all we're doing. We're finding out what this voltage is, and I'm subtracting the two voltages. Once you do that, you will realize you'll get 4.47, and that's coming up to be the same thing over here. V lost is 4.47 volts. So now I know I can just use PIV in this case. I have a V and I have an I. In this blue, I did not solve for R, so I will not use P equals I squared R, or V squared over R, because I did not solve for the R. I did solve for the V though. I could do IV. I will do the same thing, 0.999 times by 4.47, and you will get the same answer, it's actually 4.47, I can't remember where it was, 47, roughly that, so it becomes 4.46 as well, and it rounds up to 4.47. So that's two different ways to get the same answer, 4.47. You do whichever you're comfortable with. Alright, I'm going to stop it there.